Sorry. Thank you.
Okay, our next speaker, Henrik Bengtsson.
Okay.
I'll let him get straight on. Thank you.
Thank you so much. So, the most important thing first. I don't know, I have acknowledgement at the bottom, and I couldn't decide in what order. So let's start at the bottom. I want to thank the R Core. I've been working with R since 2000. I want to thank CRAN team. I want to thank all the developers that develop all the packages and all the users and the whole community. It's just lovely and it's awesome. So thank you very much. I do want to thank the organizers for inviting me here and for a very lovely workshop and conference. I also want to mention our consortium. They are funding this project this year for my future work. And that part is about standardizing testing for this framework and formalizing the specification. I'm not going to talk about that more. So I'm here to explain you the future package. I'm going to start my timer, by the way. How you can, in a very easy way, parallelize and distribute computations in R. And the first question we ask is, like, why do we parallelize software? So a very common one is like, I want it to finish before I get home today. So that's the wall time. You can parallelize things. We also do it when we sometimes we don't have enough memory to run it on one machine, so we need to split up in multiple tasks and run them either sequentially or parallel on other computers. A third reason is like it's too expensive to transport the data back to your place. Astronomers has this thing, people in genomics has this thing. I'm not going to talk about that part because it's not really covered by the future package. So let's start with some formal history and theory. So I didn't invent the futures. I guess I reinvented it, and eventually I found that it was coined in parallel back in the mid-70s. So a future is a programming concept, an abstraction for some kind of value that you want to be using somewhere in the future, a little bit later. And this value is a result of evaluating an expression. It's like 1 + 2 becomes 3. And the state of this future can either be unevaluated or evaluated. And that's an unknown state, but when it goes from unevaluated to evaluated, it's done. So let's think about it this way. In R, we have assignments operators. So we assign an expression, 1 + 2, or more complicated function calls, etc., to a variable. So the way you can think about it inside R is that R sees this expression, runs it, and immediately assigns it to a variable. So the analogy, if you do future, you actually split out those two steps, and you get that control at the R level. So you say, I have this expression, make it a future. I don't need a value right now, but I'm going to hold on to this reference to this future. And then I can do other things. You don't disturb me, you run it in the background if you want to. And when I need it, I'm going to ask for the value. So think about that. I'm going to hand out 2 futures here. Someone with a laptop. I see one person with a bright screen. I get it to both of you. So I handed out a future A and a future B there. Okay. So let's take a very simple example. We're going to summarize the values from 1 to 100. Of course, they're like shortcuts and things. But imagine we have a very slow function from doing this. So we can, instead of doing it sequentially 1 to 100, we can split it up in 2 tasks, 1 to 50 and the rest 51 to 100. And here is like how you do this with future package. You load the package, and then I'm having this expression saying I want to run it in parallel. And here is how you do it. So imagine now this slow sum function takes a minute to run. When you do this in R, it immediately returns to the prompt. So now you can do other things here. But in this case, it started doing stuff in the background. So that's one of the futures down there. And then the other one is this one. And I say, I want to do this, and it immediately gets back. So now these start ticking, and it takes a minute for them. And we can do things at our prompt, and I can play around here. So now, 55 seconds later, now I ask, give me the value. And of course, they are not done, but in 5 seconds they're done. So I can get them back. See? And what I'm shortcutting here is like I'm actually taking two values at the same time. So there's like lots of theory there too. So the first value here becomes 1275. And then the other one becomes 3,775, and then I can take the sum of both, and I get the sum of 1 to 100. But I paralyze this task now. So this is the explicit API, when you have a future function and a value function. Thanks to the beauty of R, and everything I'm doing here is like no magic hack. I'm using pure R code to do everything here. There is a concept called promises or delayed assignment, and it allows to do this very beautiful thing. You can do a future assignment of this expression, and you want to assign it to this variable. So it's very similar to the original assignment operator. The key here is like, don't touch this variable unless you really need it. So maybe you need it later. But as soon as you touch it and try to open it, then it might wait for it to finish. But it allows you to write things, the same thing, like this. So it almost looks like regular code. But what happens when I do the A and the B here, they spawn up in the background. And then I'm still at the prompt. And only when I ask for the values, it brings back it. And then they become regular variables. And if I keep asking for A and B, it's like regular variables. So that's, I call it the implicit API. Okay, so I showed you how to do it in parallel. If you don't specify anything, everything is done sequentially. That's the default. Some people might have sit in an office on the local network. You might have different computers. And you say, hey, I want to use these computers. And it's very simple. You just, if you have SSH into these computers, that's literally all you do. You specify the host names. And in the background, it sets up 3 workers on these machines. You can also do this remotely. And I've done it so it avoids firewall problems too here. But it's basically everything of this is using the parallel package. So you can have 2 machines like running in Australia. Of course, it takes a little bit of a while to bring the values back afterwards, but that's you can do this, and it works like this. So key here is like, as a developer, you don't have to worry about this. This is the user's decision. I'm going to repeat this many times. Your code will always look the same. So that's the thing. And it will always work the same. There are lots of tests going on here, and it makes sure, regardless where and how, it works the same. Okay. So the package is on CRAN since 2.5 years, I think. It has a much longer history in-house, and it grew out of different things. The idea is it defines a very simple API with, I call it atomic building blocks for parallelization or asynchronous processing. It builds on top of the parallel package. I also have a global package that builds on top of code tools to identify what variables do you need to export to Australia in order to actually evaluate the expression over there. And that's all taken care of. It's very easy to install, less than 0.5 meg total installation. I've been running it on Cancer Center research where we process like literally petabytes of data now for this system. So people ask me, is it production ready? And I say, yes. Okay, so why the future? I already touched a little bit on this, but we have a lot of great frameworks for doing parallelization, and some comes with the R installation. So if you go back to our summation problem, there are these MapReduce approaches where you have, if you have the 1 to 50 and 51 to 100, you can put that in a list, and then we do an lapply on that and call our function, and back we get the results from these 2 expressions, but of course this is not parallel. So this one that people try the first is probably the MCL apply, because this works everywhere, you think. So if you're on Mac and Unix and you do this, you're basically telling Windows users too bad. Because if a Windows user runs this, you only get sequential. So that's a downside. And that's not a problem with R, it's the operating system. It's using forked processes, so you can't do it. So if you want to support more, you'd use the cluster and sockets and then open up background R processes and communicating. So this is the language how you do that. So you also have like a par-L apply and has the concept of L apply. But the point here is like when you as a developer pick one of these, you kind of lock in what the parallelization framework will be for the future. So that's one thing I want to solve with the future package. So and also when you start, you don't have to make the decision. So with the future framework, just use this and then you can procrastinate that decision. And you give all the power to the end user. So the key is developer decides what to parallelize, user decides how and where. And then it's easy to like add new backends to support this. I'm going to mention the batch tools, future batch tool package. There's also CallR and more things are coming. So I also want to quickly mention this thing about globals and exported value. So it's working almost all cases. There are, of course, ambiguous cases, exceptional cases where things doesn't work, but basically in all cases it works automatically. So you don't have to worry about what data objects do I need to export to this computer and stuff. That's taken care of. Because in this example, slow sum might be sitting on my computer, X is clearly sitting on my computer, and those two things needs to be exported. If slow sum is part of a package, then it's clever enough not to export the package, but make sure it's deloaded the package on the other end. And if you don't like this, or you run into these very few corner cases, you can always manually guide it. Okay, so I work at University of California, San Francisco, which is a medical school. I'm a statistician working in the Cancer Center Research Institute. So we process a lot of genomics data. So all this grew out of these needs. And it's not enough for us to parallelize on one machine or 3 machines. We have many research groups with many users that need to do stuff all the time. So we have called HPC clusters. We basically, you submit jobs to a queue, and then you wait in the queue, and off it goes. And we're talking about 5,000 to 10,000 cores, several hundred computers. So there's a very nice package called batch tools. Been around for a long time, and it's stable. There are other nice HPC cluster tools, but this is the one I know the best. So it allows you to abstract away the things you do have to do manually for us. And then what I did, I wrote a few lines of code on top of that to implement the future API. So basically now, when you have this package too, you can have all the parallelization from the parallel package and also the batch tools and all the schedulers. So that's the same code to sum of 1 to 100 in parallel. And what goes on when I do A and B there, it actually takes that expression, wraps it up, put it to the job queue, waits for running, and I get it back. But you see, your code doesn't change. And this works. And this is a real example. It's we have 100 cancer patients. Each data sits in a file, raw data, 200 gigs roughly per file. It takes 10 hours to just do one step per patient. So this is like 42 days of work if you run it sequentially. So of course you want to parallelize, and with this simple construct of futures, you can use a regular for loop, and you say parallelize within that for loop. And it runs, and it works. And of course I choose, or the end user choose how to parallelize. So We only used future value in this very low building blocks. But then, of course, we can make a higher level, more natural API, so we can build on top of this. So an obvious one is like, let's take base R's, L-apply, T-apply, S-apply, V-apply, and futurize them. So I implemented this package. It's also very small changes to the core code in base R. So future L-apply, and that's the only thing when I implement these front ends. I don't have to worry about where, because the future API takes care of that. So if you have this L-apply for my 100 patients, that's the 42 days. And all you need to do is just put the future underscore in front and replace that function call. And now it's parallelizable on whatever system the user has. Okay. And you know about the for each package. It's a very beautiful abstraction of parallelization. And you can see it's a highly dependent package in the CRAN packageverse. And that's a proof of success, and it's a proof of like there's a big need for this. So there you have things like do parallel, do MPI, etc. backends. So what I did here too, I just took like a small wrapper. I wrote the do future. The first iteration was literally like 20 lines of code. And that way I open up the whole future API on the backend to whoever runs for each code. And this opens up also if you have these compute clusters and schedulers, now you can use all your for each on those environments. So that's an alternative to do a for loop here now instead of the L-apply, but it's the same idea. So there are like 1,200 packages that uses for each already, and all of these can now use these backends. And if you use Caret, for instance, you can train this model using your compute cluster. And speaking about testing, I'm part of my release schedule. I'm testing all the example and test code in Caret and a few of the major packages to make sure everything works and global variables automatically identified. So that's what I do. Okay, so let's see how are futures otherwise used too. So one thing that's been coming out this year is from the R OpenSci project now. It's basically make files in R. It's a very interesting thing. You specify what task you want to do. You want to read in your data file. You want to transform it a little bit. You want to plot it. You want to fit a model, and then you want to put it in a report. And you just do make this. And they say make this with futures in the background. It will allow to parallelize. So here futures are used inside. And basically, it goes through this, it takes care of what's done and what hasn't been done, and when it gets to this point, it knows I can do this in parallel and run it. And then, as we heard on Monday, Shiny. So Joe Sheng, he announced on Monday that any day now they will release the next version. And that means that, I haven't checked this morning actually, so basically you can do things asynchronous in the background and non-locking in Shiny now. And futures are used internally there. Quick summary, unified API, portable code, you don't have to worry about it, same everywhere. Worry-free, I try to make it. Developer decides what to parallelize, user decides how. Beginners, advanced users, I think everyone can be happy there. I didn't talk about nested parallelism. You can have a nested layer of workers. It protects against explosions. It doesn't paralyze code. It's easy to add new backends and front ends, so please work on that if you want to do that. There is promising work coming on that end too. And for those who use futures, these are the common feature requests. I want to capture standard output. Even if it's running in Australia, I want to be able to see that on my machine. Benchmarking, timing, and memory, that will come. And killing futures. Sometimes something goes wrong and you want to be able to stop it from your local machine. Thank you so much.
How that sound? Yeah. Thank you very much, Henrik. Have we got a question or two? Yeah, I'll come down. Hang on.
Thank you for a great speech and a greater future package. I got a case. Sometimes we have Shiny application and there are very heavy calculations which may take hour to finish. And is it possible to run that calculation using a future package? And then close the Shiny app, and after rerunning the Shiny app, is it possible to
restart it?
To get the return object from that future expression.
So yes, that I would put that as a task for a backend. I don't think there's a backend right now that can restore. Maybe the batch tools can do that. But that's where that should solve. But conceptually, it should work to recover things that you shut down last week and get back up and running. Yes.
Okay. Thank you.
Thanks for the question. I'll just, Dennis, if you want to, start setting up. And then I think Robin had a question.
Hi, thanks for an amazing talk. And I just tried that new operator, yet another one. I don't know if there's a short key for it yet, but it definitely works. So that's amazing.
I'm glad.
The question is actually about Drake. So I have this big project, and I'm thinking, it would be nice not to have to rerun the steps previously. So I set up my Drake thing. I read the README, and then I was like, I'm spending a whole day setting up Drake when I need to finish the project. So the question is quite simply, at what size of project do you think using something like Drake, obviously in synchrony with future, becomes worth it? How do you manage that balance between complexity of setup and the benefits? That's the question.
I mean, I think that's up to every user, but it's the same with R Markdown and all these things. It's like, what's your workflow? And eventually getting into a work pattern, and it's like, it's worth spending a little bit of overhead, and you get savvy with it. So you just have to find out. I guess that's the answer. You pick your favorite level of complexity. Yeah.
Okay, can we thank Henrik for his nice talk?